Hello, welcome to section 3.4 of our torsion lecture, which is about power transmission. Shafts and tubes having circular cross-sections are often used to transmit power developed by a machine, usually a motor. This transmitted power allows the rotation of the shafts and of course the movement of other parts of the assembly, for example, gears. The stress developed in the shaft depends upon the power transmitted by the motor and the rate of rotation of the connecting shaft. In this photo, the chain drive transmits the torque developed by the electric motor to the shaft. Shafts are subjected to torques that depend on the power generated by the machine and the angular speed of the shaft. Therefore, power transmitted is equal to the torque experienced by the shaft multiplied by the angular velocity of the shaft, or it is also equal to the torque experienced by the shaft multiplied by 2 pi multiplied by the frequency of the motor. Power can be in the units of watts, foot-pound per second, or horsepower. For angular velocity, we have rod per second. For frequency, we have cycles per second or hertz. Let us solve sample problem 3 for us to have a better understanding of torsion of shafts used in power transmission. 3 shafts and 4 gears are used to form a gear train that will transmit power from the motor at A to a machine tool at F. Bearings for the shafts are omitted in the sketch. The diameter of each shaft is as follows. The diameter of AB is equal to 16 millimeters. Diameter of CD is equal to 20 millimeters. Diameter of EF is equal to 28 millimeters. Knowing that the frequency of the motor is 24 Hz and that the allowable shearing stress for each shaft is 75 megapascals, determine the maximum power that can be transmitted. Since this problem involves a gear train, which is usually tackled in most power transmission problems, let me first discuss meshed gears. Gears are toothed wheels which are used to transmit force to other gears or toothed parts by meshing with minimal slip. In meshed gears, there are equal but in opposite tangential forces in between gears. Knowing that torque is equal to force times rho, or the distance of the force from the axis, force is just equal to torque over rho. With this, we come up with a relation between the torques from the two meshed gears. Torque at A over the radius of gear A is equal to torque at B over the radius of gear B. From kinematics, peripheral motions of the two gears are also equal. So we have the radius of gear A times the angle of rotation at A is equal to the radius of gear B times the angle of rotation at B. In this problem, we have gear B meshed to gear C and gear D meshed to gear E. Applying the concept of meshed gears, gear B has a radius of 60 millimeters, while gear C has a radius of 150 millimeters. So we now have equation 1 showing that the torque at gear C is equal to 2.5 times the torque at gear B. Gear D also has a radius of 60 millimeters, and gear E having a radius of 150 millimeters. And now, we have equation 2 showing that the torque at gear E is equal to 2.5 times the torque at gear D. Now we have already established the torques in between gears. Next is the computation of the allowable torques for each shaft using the torsion formula. We must see to it that the power transmitted will not cause the shear stress experienced by each shaft to exceed 75 megapascal. Case 1. Maximizing 75 megapascal for shaft AB, we have an allowable torque of 60.31857895 Newton meter. Case 2, maximizing 75 megapascal for shaft CD, we have an allowable torque of 117.8097245 Newton meter. Case 3, maximizing 75 megapascal for shaft EF, we have an allowable torque of 323.2698841 Newton meter. The power transmitted from the motor produces torque A, which is also the torque in shaft AB and gear B. To get the torque in gear C, we must multiply T sub B by 2.5. T sub C is also the torque in shaft CD and gear D. In order to get the torque in gear E, we must multiply T sub D by 2.5 to get T sub E, which is also the torque in shaft EF. Let's go to case 1. By maximizing the torque at shaft AB, which is also the torque in gear B, T sub C is equal to 150.7964474 Newton meter using equation 1. This case fails because the allowable torque for shaft CD is only 117 Newton meter. Going to case 2. Maximizing the torque at shaft CD, which is also the torque at gear C, T sub B is equal to 47.1238898 Newton meter using equation 1. This has a check mark because it is below the allowable torque of shaft AB, which is equal to 60 Newton meter. T sub CD is also the torque at gear D. T sub E is equal to 294.5243113 using equation 2. This also has a check mark because it is below the allowable torque of shaft EF, which is equal to 323 Newton meter. Finally, for case 3, maximizing the torque at shaft EF, which is also the torque at gear E, T sub D is equal to 129.3079536 Newton meter using equation 2. This case fails because the allowable torque for shaft CD is only 117 Newton meter. After case analysis, we must use case 2, maximizing T sub D in order for us to solve for the maximum power that can be transmitted from the motor. Using case 2, we can now solve for Pmax by multiplying the torque at A from case 2 by 2 pi and by the motor frequency. T sub A using case 2 is equal to 47.1238898 Newton meter times 2 pi times the motor frequency, which is 24 Hz. Therefore, the maximum power that can be transmitted from the motor is 7,106.1152 watts. Thank you for watching.